19 part 3. So in the previous two parts, we talked about how to use the minimax algorithm or the alpha beta pruning to solve a game. So they are basically like DFS. So we probably need the A-star equivalent of the BFS search, DFS search. So we're going to add a heuristic. And here we don't actually care about whether the heuristic is overestimating or underestimating. They are not going to give you the precise optimal solution anyways. We just want to shorten the computation time because, for example, for chess, there are so many states, so we don't want to go through actually all of them. We don't want to precisely get the best solution. We just want to get one that hopefully more likely is going to lead to the computer winning. So that's the idea, and we're going to call the heuristic, the H function, the static body valuation. So it's basically a value for all the non-terminal states. So it's the same idea as for the non-goal states. We're going to have an estimated approximation of the cost from that state to the goal state. Here, we're going to have a cost, an estimation, approximation of the value at those states without actually computing the maximum of the subtrees or the subgames. So if we're talking about 1, 0, minus 1 of the values, then it just reflects the probability of winning. So that would be one way to specify the heuristics. And it should be, of course, it should be easy to compute given the state. So a state is basically a board configuration for a board game. So if the static body valuation is x for one player, the other one should be minus x. Sometimes if we want to use probabilities, then it's just 1 minus x. It's the same thing. One person is maximizing, the other person is minimizing, so it doesn't matter if we add a constant. And if we go to the end, then the evaluation should be consistent at those terminal nodes. So we don't need them anyways. So we only use them for the internal nodes. So for the chess, there are many variables that we can use to represent the static body valuation. So given a specific configuration, we can compute something like the material mobility. I don't actually know these terms, so I think material is basically the total value of the chess pieces we have on the board. Mobility is how much we can move. I don't actually know how to measure them, but they are from some domain expert knowledge, and they are used to kind of guess the probability of one player winning. So we're going to use them, and we're going to use them as features. So when you see the word features, you know we're going to put a neural network on it. So yes, we are. And the first thing, before we go to neural network, we are going to use IDS instead of DFS. So instead of go through the end, we're just going to stop at a level. Say this is our level, current level D. We're going to do, say, something like DFS, like this. And then we're going to cut it off and use the static body valuation values for these internal nodes. We know that they can continue, and there's a subtree, basically large subtree after this, but we are going to ignore that subtree and just use the static body valuation here. And if, for example, if we allow the computer to think for a few seconds, and then we can just gradually increase D, and to say after this we can use the static body valuation for our larger D plus 1 level, and then we use these, and then we can recompute the same thing until basically the time is up. And we are, as I said, we're using these heuristics as if they are the actual values, which they are not. They are just approximations. And how are we going to learn these? Of course, we're going to learn it using the training data that are basically the games from professional players, and we can use the features that I talked about, so basically from experts for that particular puzzle of that particular game, or we can just use a convolutional neural network to kind of learn those features, and then we can train again on those training data from games between professional players. And the other thing we can do is we can use something called Monocot Research to actually make these guesses a bit better. So we can simulate the game by just letting the players choose random moves. So, but there's a problem. If I always choose random moves, none of these are optimal. So we can just choose the random moves for the first few iterations, and then given these random moves, we can actually make a guess of which branch is better than which. So for example, let's start with a game like this, and suppose we want to stop here, and then we can just try a few of them, and then we know that if I choose this branch, given these random, completely random games, we know what's the probability of winning if I choose this branch, what's the probability of winning if I choose the other branch, and then we can focus on the better or the worse per branch. Given, suppose we are the max player, then we are going to pick the branches that often leads to the max player winning, and so on. So we can start by exploring the space. So basically, we're using completely random choices, so we can visit as many successors as possible. And then after a while, we could switch to exploitation. So we could keep track of the average win rate from those exploration that we did earlier, and then exploit that fact that it's more likely to lead to either winning, one player winning or the other player winning, and then we can explore those sub branches further, so we can get a better estimate of the value at the root of this subtree. So that's the idea, that how we actually trade off this, how much we explore, how much we exploit. I should have talked about this in the reinforcement learning lecture. So in the reinforcement lecture, last year I talked about some problem called the multi-arm bandit problem, and there is an algorithm called the upper confidence bound algorithm that's used as a reinforcement technique to basically trade off exploration and exploitation. However, I didn't talk about that, so you don't know what this formula is, so I'm not going to talk about it here. And when I actually record the reinforcement learning lecture, I'll go back to this and talk about this again. And so basically, the main idea you need to know is we are going to combine exploration, basically trying new stuff, trying unvisited nodes, and exploitation, basically going through the branches that are more likely to lead me to winning. So that's the main idea here, and we're going to use some kind of mathematics to do that. And for the AlphaGo algorithm, it is actually using Monocot Research, and it also combines the convolutional neural network to combine these static bot evaluations. So basically, it treats the Go bot as an image, so there are black and white pixels, and it trains a convolutional neural network on training data given by professional players and experts.